In this video, I'm going to talk through a dimensional analysis past paper question as a full worked example that covers pretty much all the different approaches you need to know to attack any dimensional analysis problem. So part one does just say write down, so we could say the answer, but I'll talk through where they're coming from. So dimensions of velocity, if ever you're not sure for something, so dimensions of velocity, you probably are able to write down straight away. But if you're not sure, think about the units. You should be confident that the units of velocity are meters per second. So the dimensions of velocity are a length per unit time, or LT to the minus 1. So make sure when you're given dimensions, two things to watch out for notationally. Firstly, these square brackets, which should be read as dimensions of. So don't write V equals LT to the minus 1. We're writing the square brackets of V or dimensions of V equals that. And then using capital letters, the only dimensions you're going to be working with are going to be L for length, T for time, and capital M for mass. So everything's going to be in terms of those three letters there. Okay, next one then. So dimensions of acceleration. Well, if we know acceleration is measured in meters per second squared, then that's a length per unit time squared, so LT to the minus 2. And dimensions of force isn't necessarily one you'll always know off by heart, although I'd recommend you do. But if we're stuck, well, it's going to be dimensions of mass multiplied by dimensions of acceleration, because we know the force is mass times an acceleration. So dimensions of mass is just m. Dimensions of acceleration we've already got at LT to the minus 2. So dimensions of force is just mLT to the minus 2. The second part, we're then given an equation, and any equation that's correct any formula must be dimensionally consistent. So if we're being told this, and we know our dimensions of force, our mass, and our distance apart, which is r, then we should be able to get dimensions of this constant here, g. You can either take dimensions straight away, or you can rearrange. I'd recommend rearranging first here, because it should make your life easier in terms of the order you're going through. So if we start by rearranging to get g equals, then we'll get that g is equal to f r squared over m1, m2. And then because we need this to be dimensionally consistent, we can then say that the dimensions of g must be equal to the dimensions of fr squared over m1, m2. And this is the same as saying the dimensions of f multiplied by the dimensions of r all squared. We can even take the squared out of that over the dimension of m1 times the dimension of m2. Now, most of these are quite nice, because dimensions of force you've already got from part 1. We know is mLT to the minus... Sorry, it's not that. mLT to the minus 2. Dimensions of our r, which is distance, is just going to be length. So that's length squared. And then it's over mass times mass, or mass squared. This is a show that. So I wouldn't jump, even though you could, I wouldn't jump from here to here in one step. I'd have 2 steps here. So what should we do to deal with this? Let's just say that this is equal to, let's tidy that top bit first. So that's going to be m L cubed t to the minus 2 over m squared. And then we can say we've got m over m squared. So that's going to be m to the negative 1 L cubed t to the minus 2. And on most short arc questions, I'd always say write a conclusion. In this case, this is basically our conclusion. We've got dimensions of g equals this. If you want to state it as a sentence, there's no harm in doing so, but this should be more than sufficient. Okay, I'm just going to grab this and move it down, because this is where it starts to get trickier in this next bit of the question. So we're told that we've got dimension, that the value of g is 6.67 times 10 to the negative 11 when we're measuring in SI units. By SI units, we mean kilograms, meters, and seconds. But obviously, they're not the only units that we might choose to measure in. So now g is, so that's going to be 6.67 times 10 to the minus 11. Now, because we knew our dimensions of g, because we know our dimensions of g are m to the negative 1, L cubed, t to the negative 2, this is really saying this is in meters to the negative 1, and then, kilograms to the minus 1. Let's try that again. kilograms to the minus 1, meters cubed, and then seconds to the minus 2. And the problem is we're being asked to change this to be in terms of pounds. So lb for pounds here to the minus 1, feet, so feet cubed, and at least the seconds are staying the same here. We're not changing that bit. Now, it's easy to get these conversions wrong way around or ignore powers. So I'd always recommend just making sure you're happy with how you do a conversion here. So if we want to change from 1 kilogram to pounds, then what would we do? 1 pound is equal, as we're told, to 0.4536 kilograms. So if we've got 1 kilogram and want to get to pounds, we need to divide by 0.4536 or multiply by 0.4536 to the power of negative 1. So if we were changing from kilograms to pounds, we'd divide by 0.4536. But we're changing from kilograms to the minus 1 to pounds to the minus 1. So we're going to want to divide by that thing to the minus 1, which is the same as multiplying by 0.4536. And then with the meters, let's do the same thing with meters. So from 1 meter to feet, what would we do? Well, from a foot to a meter, we'd multiply by 0.4308. So here we'd divide by 0.3048. And we've got meters cubed though. So rather than just dividing by that, we're going to divide by that scale factor cubed. So we're going to divide by 0.3048 all cubed. So there's 2 steps here. You can do them in 2 steps if you want. As long as you're being clear, you can do it in 1. So you're taking your value, you're multiplying by 0.4536, and then you're dividing by this 0.3048 cubed. Seconds is staying the same, so we don't need to worry about that. And if you do that calculation, you should find you go 1.07 times 10 to the minus 9 in these new units. Okay, the next part of this question, we're given a new formula here, and we're asked to show it's dimensionally consistent. Any show that question, we need to make sure we're being really careful with our layout here, so I'm going to be as careful as I can, showing you exactly what you should do for the marks here. We want to show the dimensions of V are equal to the dimensions of the right-hand side. So what I'm not going to do is write dimensions of V equals dimensions of square root 2 GM over R, because I'm assuming what I want to show is 2 straight away. Instead, I'm going to consider the dimensions of both sides. So I'm going to say that I'm going to look at the dimensions of the left-hand side, which is just equal to dimensions of V. I'm always going to write dimensions of V. You could get away without writing dimensions of LHS if you want. And that's LT to the minus 1. We already know that from part 1. And then let's have a look at the dimensions of the right-hand side. So the dimensions of the right-hand side, we want to look at the dimensions of root 2GM over R. Now, when you're dealing with this, we can take, so the square root is doing it to the power of half, and we can take that out of our dimensions. So I'm going to say we're going to have the dimensions, well, the dimension of 2, this 2 is just dimensionally, sorry, it's a dimensionless constant, so that 2 is going to disappear, and we're just going to get our dimensions of G, dimensions of M, over dimensions of R. Now, what do we know? Well, we know our dimensions of G from before was M to the minus 1, L cubed, T to the minus 2. We know our dimensions of M are just M because it's a mass, and our dimension of R is a length. So we've got this to the half. Again, it's a show, so I'm going to be as careful as I can. I could try and do this in less steps, but I'm never going to try and skimp on steps when it's a show that. So let's deal with the numerator first. The m's are going to disappear because we've got m to the negative 1 times by m. So I've got L cubed T to the minus 2 over L to the half. Now I can deal with the next thing, and I'm going to have L squared T to the minus 2 because L cubed over L is L squared to the half. And this gives us LT to the minus 1. Now let's look. Good, that's what we're hoping. We wanted it to be equal to dimensions of V. So I'm going to put dimension equal to dimensions of V. Like I say, you could get away without writing dimensions of LHS here, but I'm just being for completeness here. It's a show that, so I should finish with a conclusion. So I'm just going to say, so the equation is dimensionally consistent. Whatever you're being asked to show in a show that, make sure you just conclude that you've shown it. There's often a mark for this, and it's a really silly mark to throw away. It's an easy mark to pick up, but if you're lazy, you won't get it. So the rest of the show is dimensionally consistent. I should have wrote formula, I suppose, really. I doubt it'll be that harsh to penalise me for that. And then the final bit's a really classic sort of question you get in dimensional analysis questions here, where we're being asked to use a formula, use a sort of formula to work out what these powers must be to make it dimensionally consistent. So we're always going to start by saying, well, any formula that's correct must be dimensionally consistent. So we must have the dimensions of t are equal to dimensions of the right-hand side. Now, let's just write it all out for completeness here. You could probably get away without this very first step. The k's a dimensionless constant, so that's going to disappear, and we're just going to have the dimensions of g to the alpha, dimensions of m to the beta, and dimensions of r to the gamma. Now, on the right-hand side, we've got dimensions of t. I just capital T because it's just a time, and now we can start forming some equations using what we know. So we're going to get t is equal to dimensions of g, once again, is m to the minus 1, L cubed t to the minus 2, all to the alpha. Dimensions of our mass are just m to the beta, and dimensions of r, that was just a length, so that's L to the gamma. And now we want to just simplify that right-hand side and collect our m's, collect our l's, collect our t's. So our m's, we're going to have m to the negative alpha and then plus beta. We're going to have L to the 3 alpha plus gamma, and we're going to have t to the minus 2 alpha. Now we're going to get three equations here. We could look at our m's first, we could look at our l's first, we could look at t's first. Because our t on the right-hand side only has an alpha and not a beta or a gamma involved, that's going to be the nicest one to start with. No, the left-hand side is really just t to the 1. So we can say that 1 is equal to negative 2 alpha, and alpha is going to be equal to negative a half. We can then look at our m. Now, on the right-hand side, we don't have any m. If we wanted, we could write it as m to the 0, because m to the 0 is just 1. So we're going to get our 0 is equal to negative alpha plus beta. And from there, we can then say, well, quite happily here, say that we're going to get beta is equal to alpha, which is equal to negative a half. And finally, looking at our l's, again, it's L to the 0 on the left-hand side, so it's 0 equals 3 alpha plus gamma. Sorry, that's a plus. So we're going to get 0 is equal to minus 3 over 2 plus gamma, and we're going to get gamma is equal to positive 3 over 2. And that's our final answer. Thank you very much.